Hello. Today we're going to talk about complex numbers. Um, so I've done this webinar before several times, so you can always go back and watch usual. So today I've chosen 8 questions that are quite on the medium to easy side today. So if you want some harder things, you can watch some of the previous webinars. But yes, I am assuming you're already familiar with complex numbers. Therefore, I won't be explaining the basics. I'll go straight in. Just a quick reminder that of the types of numbers that we have. So we have natural numbers. We can draw it as a Venn diagram. Natural numbers and whole numbers include natural numbers, of course. Any natural number is also a whole number. Then we have rational numbers, numbers that can be written as fractions. Then we have real numbers. And we have complex numbers. Complex numbers is the overarching. So any number is a complex number. Well, unless you do some exotic numbers. Yes. Anyways, some exotic algebra like bicomplex. I'm I'm not there. This is not my field. But yes, any natural number is a whole number. Any whole number is a rational number. Any rational number is a real number. Any real number is also a complex number. Okay, uh, perfect. A complex number is typically written as x plus iy, where x and y are real, and I is the square root of -1, of course, or rather I squared is -1. It's imaginary 1. Show that for any complex number, x plus iy, z times z star. So z star is the complex conjugate. So if z is x plus iy, then z star is x minus iy. It's the complex conjugate. Complex conjugate. And therefore, we multiply them. So z star is equal to x plus iy multiplied by x minus iy, and that's equal to x, we open the brackets, x squared minus ixy plus ixy minus I squared y squared. Now these two cancel out, and we know that I squared is -1, so that's x squared plus y squared. But what is modulo z? Modulo z, as you should know from your school course, y, if you have a complex number z, modulus z is the length of the vector drawn from the origin to point z, x plus iy. And therefore, if you do a right angle triangle, this is x, this is y. Modulus z is square root of x squared plus y squared. And obviously, you can see that z star, well, you can write that z squared, modulo z squared, is x squared plus y squared. Obviously, that hence z star is modulus z squared. A very important result. Okay. Hence prove that the modulus of z, well, yes, obviously, then z can be written as modulus x squared plus y squared. Okay. Solve. This is a linear equation. And we need to find z. So of course, the first thing that we do is well, we could just divide by 2 minus 3i. But I'm going to do it in a slightly different way. I'm going to multiply both sides by 2 plus 3i. Because I know that if I multiply 2 minus 3i by 2 plus 3i, I get a real number on the left. So that's what I'm going to do. It's 2 plus 3i multiplied by 2 minus 3i multiplied by z equals 5 plus 7i multiplied by 2 plus 3i. Opening the brackets, so that's 4 minus 6i plus 6i plus 9 times z equals, let's open these, so 10 plus 15i minus plus 14i minus 21. And therefore, that is that even possible? It must be. Yeah, 21. Yeah. Okay, so here we have these cancel out. 13z is negative 11 plus 29i, and z is equal to negative 11 thirteenths plus 29 thirteenths I. Cool. And obviously that this is x and this is y. All right, so hopefully, okay, on a scale of 0 to 10, how well do you understand these two questions? Um, cool. Excellent. All right, so next one. If z is 3 minus 4i, find 1 over z. 1 over z is 1 over 3 minus 4i. So we multiply top and bottom by 3 plus 4i, and we get, on the bottom, we get 9 plus 16, so that's 25. And on the top, we get 3 plus 4i, which is 3 25ths. Yes, 3 25ths plus 4 25ths I. Okay, that's A, B. Where asks Z divided by Z star. Oh, interesting. So that's 3 minus 4i divided by 3 plus 4i. So we multiply top and bottom by 3 minus 4i. And we get, so here we get 9 plus 16, 25. And here we get 9 minus 12i minus 12i plus, no, minus 16. Yep, and that's negative 7, negative 24i divided by 25, which is negative 7 over 25, negative 24 over 25i. Okay. C. The point representing each result on an argon diagram. Okay. So the first value is 3 minus 4i. 3, 1, 2, 3, 1, 2, 3, 4. So that's z. 1 over z is here. 3 25ths, 4. So somewhere here. 1 over z. and z over z star minus, so that's going to be somewhere here. So z over z star. There must be some significance to it, but I can't see it. So let's just assume the three questions are unrelated. Anyways, roots. One of one of the tricks you can do with people is the following. So apologies. Trick. Let's start with the number 1. 1 can be written as square root. No, actually, well, it doesn't matter where we start. Okay, let's start with -1. -1 can be written as I squared. I squared is square root of -1 squared, which is square root of -1 multiplied by square root of -1, which is square root of -1 multiplied by -1, which is square root of 1, which is obviously 1. I've just proven to you that -1 is 1. And if somebody tells you you owe me $100, £100, you can say, well, I can prove to you that -1 is the same as 1. Therefore, -100 is the same as 100. So you owe me £100. Okay. So what's wrong? What's wrong with the thing? Well, the problem is actually in the final step. Because is it the final step? Well, yeah, pretty much. Pretty much in the final step. When you talk about complex numbers, square root is not a one-to-one function. For real numbers, square root is a one-to-one function. F of x is square root of x. It's a one-to-one. One-to-one. But if x is real. But if x is complex, then it's not a one-to-one function. It's actually a one-to-many function. F of x equals square root of x is a one-to-many function. Basically, what that means is that square root of -1 has several values. So the final step is incorrect. Okay, but it's a nice trick. So, well, what do we do? Well, let's say we want to find square root of 1. What we need to do is, well, they say, well, let's say z is square root of 1. Yes, so z squared is 1. Okay, so Well, from here, it's very obvious from here that z is 1 or minus 1. Z is plus or minus 1. Hence, uh, square root of 1 is plus or minus 1. Okay. It gets more interesting. It gets more interesting as we will see in the next question. So find all complex roots of the equation. And there are different ways to do this. So let's first do it algebraically. Algebraically. And here we have z cubed. And I'm going to do z cubed plus 8 equals 0. I'm going to notice that z equals negative 2 is a solution. Therefore, I'm going to divide by z plus 2. Z cubed plus 0z squared plus 0z plus 8. I'm just writing it out as in a standard form. Oh, that's not how you divide. Okay, I'm doing long division. And z plus 2, like this, long division. So z plus 2, so it's going to be z squared. Z squared times that is z cubed plus 2z squared. Subtract negative 2z squared plus 0z. Z squared times that is, minus 2z squared divided by z is minus 2z. Minus 2z times that is minus 2z squared minus 4z. Subtract, that's 4z plus 8. And now this divided by that is 4 plus 4. So it's 4z plus 8. The remainder 0. Perfect. Therefore, z cubed plus 8 equals 0 can be written as z plus 2. Open bracket, z squared minus 2z plus 4 equals 0. So either z equals negative 2 or z squared plus 2 negative minus 2z plus 1 plus 3 equals 0. I hope you understand what I did here. So this is z minus 1 squared equals negative 3. Z minus 1 equals plus minus root 3i. Z equals negative 1 plus 1 plus minus root 3i. So I've got 3 solutions. First solution, second and third solutions. Does that make sense? Have I lost anyone here? Do you fully understand what I did? Okay. If I was doing this question, I would never do it that way. It's just too clumsy. I like elegant solutions. So using modulus argument. Modulus argument. So what am I going to do? So I'm going to write down the equation. Z cubed equals negative 8. I'm going to write down 8 in modulus argument form. And if I find minus 8 is here. So modulus of minus 8 is of course 8. And argument of minus 8 is of course pi. So I'm going to write down z cubed equals 8 multiplied by e to the power I pi. But who said that it is I pi? It might as well be 3 pi or 5 pi or etc. So I'm going to write plus I 2 pi k, where k is any whole number. Do you understand what I did here? Yes or no? Yes. I'm waiting. Okay, cool. All right, so now I'm gonna take both sides of the equation to the power 1/3. So that would make z equals 2 multiplied by e to the power I pi over 3 plus I 2 pi k over 3. And I'm going to write down z, the first solution, z0, is when k is 0. And that's just 2e I pi over 3. Z1 is when k is 1, so it's 2e I pi over 3 plus 2 pi 3, so it's I pi. And Z2 is 2e I plus another pi over 3, so that's 5 pi over 3. And this could be written as 2 cos pi over 3 plus I sine pi over 3, which is 2 times a half plus I root 3 over 2, which is 1 plus root 3i. This is 2 multiplied by cos pi plus I sine pi. This is 0, and this is 1, which is just negative 2, sorry, minus 1, negative 2. And this is 2 multiplied by cos 5 pi over 3 plus I sine 5 pi over 3, which is 1 minus root 3i. So I got 3 solutions. Okay, maybe it's not much faster than the previous one, but it definitely much faster for higher powers, right? If I were doing like power 7 or power 8, I would not try to do it algebraically. Well, actually power 8 I would do algebraically. Power 7 I definitely wouldn't. Okay, so that's how it works. Okay, and then if you draw these solutions on an Argand diagram, let's say this is a circle of radius 2. So the solutions actually are here. So this is negative 2. This is 1 plus root 3i. And this is 1 minus root 3i. They make a regular triangle. All right. In other words, uh, in other words, cube root of negative 8 has 3 values. Now, in real life, when you did real numbers, cube root of minus 8 is just negative 2. But no, in complex numbers, it has 3 values. So negative 2, 1 plus root 3i, and 1 minus root 3i. And that's very important. That's a very important distinction. In the complex world, things don't work as you are used to. Okay, moving on. Problem 5. Okay. let Z uh, cosine theta plus I sine theta. Use hence. Sorry, I'm just trying to see why would we do hence in here, but let's not do hence. I don't see a reason why we should. Just find. Okay, anyways. Well, there's the De Moivre's theorem, and the De Moivre's theorem says that if cosine theta plus I sine theta to the power n is cos n theta plus I sine n theta, which is really nice. Theorem. So yeah, and so problem A becomes really straightforward. So z to the power 6 is cos theta plus I sine theta to the power 6, which is simply cos 6 theta plus I sine 6 theta. Okay. It's a very useful tool, especially if you're trying to, for example, uh, find cosine cubed theta. It's, but I don't think I'll go there today. From here, you can find cos 6 theta by using binomial expansion. So what you would do is you would expand this binomially. So cos to the power 6 theta plus 6 cos to the power 5 theta I sine theta plus etc. And then that's would be equal to cos 6 theta plus I sine 6 theta. And then the you would add all the real parts. So add all the real parts, and that would equal to cos 6 theta. But I don't want to go there. This is just like an extra extra layer of the De Moivre's theorem. One of the uses of De Moivre's theorem, in fact. So B, I'm going to do the straightforward question. So z to the power 6 is 1. Effectively, what they're asking is what is the sixth root of 1? Again, if it was real numbers, the answer would be very easy. But it's not. So what I'm going to do is I'm going to write 1 as 1 multiplied by e to the power 2 pi I 2 pi k, which is equal to z to the power 6. And then I take the sixth root of both sides, so everything to the power 1/6. So that makes z equals 1 multiplied by e to the power I 2 pi k over 6. So z equals e I pi k over 3. And then you just substitute k equals 0, k equals 1, k equals 2, etc. Z0 is e to the power 0. Z1 is e to the power I pi over 3. Z2 is e I pi 2 pi over 3. Z3 is e I 2 pi over 3 pi over 3. Z to the power 4 is e I 4 pi over 3. Z5 is EI 5 pi over 3. Now, why do I stop at 5? Well, because the next one is going to be 6 pi over 3, which is 2 pi, which is 0. So the next takes me back to the start, and this cycle repeats. It's just gonna repeat itself. So I only need 6 different values. So an equation of the 6th power has 6 roots, and these are the 6 roots. Okay, so e to the power 0 is just 1. E to the power pi over 3, that's cos pi over 3 plus I sine pi over 3, which is 1/2 plus root 3 over 2i. This is minus 1/2 plus root 3 over 2i. This is negative 1. This is negative 1/2 negative root 3 over 2i. And this is plus 1/2 negative root 3 over 2i. Does that mean you can never have multiple roots of the same complex? Does that mean you can never have multiple roots of the same complex number for a given degree polynomial? I'm not sure what you I don't know what that means. Sorry. I'm trying. I've reread it a couple of times. I'm not understanding. If you have z cubed, I see what you mean. So, like, that's a good one. Well, let's see. If you have z minus 1 squared equals 0, z minus 1 equals 0, z equals 1, z equals 1. I think you can still have repeat roots. Yeah, I'm not 100% sure, but I mean, clearly you can have repeat roots. Yeah, yeah. Can you have the same repeat complex root? By all means. Look, you can create a polynomial with any roots, right? So all you need to do, if you know the roots of your polynomial, you just write down. So write a polynomial with roots uh, minus 1, 2i, I plus 3i, and zebra. So these are the 4 roots of the polynomial. And all you need to do is z plus 1 multiplied by z minus 2i multiplied by z minus, sorry, that's 1. Z minus 1 minus 3i and z minus zebra. Okay, I'm joking about the zebra. If it's, well, let's make it 1 minus 3i. Is z minus 1 plus 3i. And when you expand this polynomial, that's what you get. A polynomial with the given roots. And well, you can have an arbitrary constant. So answering your question, yes, you can have a polynomial with with repeat complex roots. Okay. Um, I hope that's what you were asking. Okay. Does that clarify things? Yeah. Okay. Because you can always make a polynomial, whatever polynomial you like, which with whatever roots you like. Okay, so we have this. So z is 2 cos. I, I don't like this form. I don't like this form of writing. So I'm just going to straight write it down as e I pi over 6. And w is 3 e I pi over 3. I want to find the modulus and argument of this. So I do w divided by z squared is going to be 3e I pi over 3 divided by 2 squared. So that's 4e I pi over 6 multiplied by 2. So that's 3e I pi over 3 divided by 4e I pi over 3. And you can see that this cancelled out, and it's just going to be 3/4. So this is just 3/4. It's a real number. Therefore, argument of w over z squared is 0. And the modulus of w over z squared is 3/4. Of course, you can write it in polar form, so as in modulus argument form. You can write it as 3/4. So w over z squared is 3/4 e I 2 pi, or e I 0. All right, so it makes sense. Number 7. Let's move on. Okay. If z is I theta, that means, oh yeah, z is I theta, then so z equals e I theta, then z to the power 1 over z is z to the power minus 1, which is e to the power minus I theta. And this could be written as cos, well, in modulus argument form, this can be written as cos theta plus I sine theta. And this can be written as cos minus theta plus I sine minus theta. But remember that cosine of minus theta is just cos theta because it's an even function. And sine minus theta is minus sine theta because it's an odd function. And therefore, we can write down as cos theta minus I sine theta. And now we just add. So z plus 1 over z is equal to cos theta plus I sine theta plus cos theta minus I sine theta. I sine theta cancel, it's 2 cos theta. So what we needed, and 2, z minus 1 over z, which is z minus z to the power minus 1, which is cos theta plus I sine theta minus cos theta plus I sine theta. That cancels, it's 2I sine theta. And that's what we needed to prove. So here we can write down that E, so hence E I theta plus E minus I theta is equal to 2 cos theta. Cos theta is E I theta plus E minus I theta divided by 2. The next one is sine, so E I theta minus E I theta is 2I sine theta. So sine theta can be written as E I theta minus E minus I theta divided by 2I. And maybe as a homework, or maybe now, I'll see if I can come up with a solution now. But as a homework, solve cos theta equals 2. Okay? Hmm. I'll just start. So cos is E I theta plus E minus I theta divided by 2 is 2. So E I theta plus E minus I theta is 4. And multiply by E I theta. So you get E 2I theta plus 1 minus 4 E I theta equals 0. It's a quadratic equation. And E I theta is 4 plus or minus square root of 16 minus 4 divided by 2, which is 4 plus or minus or something like that. 4 plus or minus 2 root 3 over 2, which is 2 plus minus root 3. Yeah, and then do something. Yeah, I don't want to basically solve this, right? It does have a solution. Anyways, number 8. Oh, this is quite easy. All right. Z. Find modulus Z. Well, modulus Z, so A, modulus Z is 1 squared plus root 3 squared. So that's 2. Argument Z. Well, to find argument Z, I always prefer to sketch. So 1 and root 3. So it's like this. But that's obvious because if this is 1 and this is root 3, this is just root 3 and 1. So it's arctan root 3 over 1. I would always say be very careful not to use this formula blindly, okay? You might get into trouble. Even though in some maths books, they tell you that modulus of a complex number is the arctan of y over x. Well, not really. You have to consider which quadrant you are in. And that's 60 degrees pi over 3. Okay, so that's easy. B. Express z to the power 4 in Cartesian form using de Moivre's theorem. Okay, so z to the power 4 is 2 multiplied by cos pi over 3 plus I sine pi over 3. And this is to the power 4. Therefore, it's going to be 16 cos 4 pi over 3 plus I sine 4 pi over 3, which is wait. Oh, okay. Right. So assuming we don't know what cosine 4 pi over 3 is. Okay. Uh, Cartesian form, de Moivre's theorem. And on the other hand, z to the power 4 is 1 plus root 3i to the power 4. And this is 1 plus 4 multiplied by root 3i plus 6 multiplied by 3 times minus 1 plus 4 multiplied by 3 root 3 minus I, and finally plus 9. Well, I to the power 4 is just 1, so 9. Okay, so I'm using binomial expansion here. So that's 1 minus 9 minus 18. 10 minus 18 minus 8. And then here we have 12 minus 12, so that's minus 8 root 3 I. Oh, lovely. So from here, if you open these brackets, it's 16 cos 4 pi over 3 plus 16 I sine 4 pi over 3. And now you can say that this thing is equal, sorry, this thing is equal to this thing, and this thing is equal to this thing. In other words, hence 16 cos 4 pi over 3 equals negative 8. So cos 4 pi over 3 is minus a half. It's the weirdest way of finding cos 4 pi over 3. Anyway, 16 sine 4 pi over 3 is equal to negative 8 root 3 without I. And then sine 4 pi over 3 is negative root 3 over 2. Brilliant. Okay. Now we're getting to some interesting stuff. So the last 3 questions are very similar to the final 3 questions from the assignment. So bear with me. Describe the locus in the complex plane of this. Now I'm going to, well, first of all, I'm just recall that argument of z1 divided by z2 is argument z1 minus argument z2. So we can rewrite this expression as argument z minus I minus argument z plus I. That's equal to pi over 3. Okay. What type of curve does this represent and how it is positioned relative to the real axis? Well, let's have a look. What is z minus I? X, I. Well, IY. If you think about it, like imagine you have Z1, Z1 and Z2, 2 points. So this would be argument Z2. This would be argument Z1. But if you want argument Z1 minus Z2, what's that? Well, you need to draw the vector Z1 minus Z2. This is the vector Z1 minus Z2. An argument of that vector is this. So this is the argument of Z1 minus Z2. So argument Z2 is the argument of vector joining Z1 and Z2. Well, Z2 and Z1. Therefore, let's take an arbitrary point. Let's take a point Z. Z is an arbitrary point. Now, if it's an arbitrary point, then this is the argument of vector joining Z and I. So this is I. This is minus I. And this vector the argument of that vector, argument of Z minus I. And now this Z plus I is this vector. Yes. And the argument of that vector, argument of Z plus I. Now this is a positive argument, but this is a negative one because it's below the x-axis. I'm gonna write minus here. But if you add them together, oh, but this vector is this vector, and this vector is sorry, this vector, and this vector is this vector. So you can see that this angle if you add them together, sorry, why do I have minus there? Is the argument Z, sorry, Z1 minus Z2. Is it? Z1 minus Z2. Z1 minus Z2. Z minus I. minus pi over 3. Let's see if we can get a slightly different result. No, it's just a second. Z minus I. I'm having the opposite sign. I'm not sure why. I'm not sure what's going on here. Minus I, Z minus I is the vector. Let's say argument of I plus 1. Argument of I plus 1. So I plus 1 is here. It's pi over 4. Argument of I from I to 1. I to 1. I to minus 1. Yeah, that makes sense. Argument of I or Z minus I. Okay, I'm a little lost here. Sorry. Oh, the sign's wrong, and I can't figure out what's wrong. What happened? Uh, so if we take an arbitrary point, so Z, and we draw, let's draw vectors Z here slightly. Okay, and this is I. This is minus I. Then this vector is Z plus I. And this vector is Z minus I. And we're told that the argument of this vector, theta, minus argument of this vector, theta 1 minus theta 2 is pi over 3. Which doesn't make any sense because this vector is it supposed to be minus? Let's see if we go from here. Like if this is Z, this is Z, this is I minus Z. That's even more confusing. Okay, let's just cheat. Okay, let's put it minus pi over 3 and let's not worry about it. Okay, right, and then everything falls back into place. So effectively, what they're saying is that theta 2 minus theta 1 is pi over 3. Okay, what does that mean? Well, if you take this angle, this is a right angle. So this is 90 degrees. So this is theta 1, and this is theta 2. And this is 90, well, pi over 2 minus theta 2. Okay. This angle, this small angle, is theta 1 minus theta 2. Is pi over 3. Theta 1. Oh, well, it's this angle. So this angle is fixed. This angle is pi over 3. And now, if I have two fixed points, I and minus I, and this angle is fixed, pi over 3, what kind of curve would point P draw? Can somebody tell me? If I were to be allowed to move point P, but keeping the angle the same, what kind of curve would I see? Does anyone recognize what curve it is? Remember circle theorems from GCSE. If you have angles in the same segment, theta, 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 theta. So if you were to keep the angle the same, it would be a circle passing through like this. And on the other side, it would be a circle like this, because the rule is still the same. And then you would just find the center of the circle. The center of the circle would be 1 over root 3. 1 over root 3. And the radius of the circle would be 2 over root 3. 2 over root 3. And same here. This would be minus 1 over root 3. And the radius is 2 over root 3. Okay, so I hope that made some sort of sense. Moving on to the next one. This one is very similar to the one in the assignment. So show that the locus of Z is a circle. Find its center and radius, and determine whether the point lies inside or outside the circle. Okay, so this is an equation where Z is a complex number. So what I'm going to do is simply I'm going to write down as Z equals X plus IY. And I'm going to do modulus of Z, modulus of X plus IY minus 3 minus I over modulus X plus IY minus 1 plus I equals 2. I'm going to multiply both sides by this modulus. Well, I can find the modulus. Remember, the modulus of a complex number is square root of x squared plus y squared, right? So it's the real part squared plus the imaginary part squared. So to do this, I'm going to write the real part separately. X minus 3 is the real part, plus y minus 1 is the imaginary part. Real part here is x minus 1, plus y plus 1, and equals to 2. And here I'm going to write x minus 3 squared plus y minus 1 squared divided by square root of x minus 1 squared plus y plus 1 squared. That's equals to 2. And square both sides, multiply by 4. So x minus 3 squared plus y minus 1 squared equals 4 x minus 1 squared plus 4 y plus plus 1 squared. Opening the brackets, x squared plus 6x plus 9, minus 6x plus 9, plus y squared minus 2y plus 1 equals 4. X squared minus 2x plus 1 plus 4, y squared plus 2y plus 1. Opening the brackets, so I get 3x squared minus 8 minus 2x 4 minus, okay, plus 3y squared, 8 plus 2 plus 10y, and then, well, that's 4 plus 4, 8 minus 10 minus 2 equals 0. And then we just need to work out what this equation is. Well, it's a circle. And to show that it is a circle, we need to complete the square. Of course, we can divide the whole thing by 3. Why not? Divide the whole thing by 3. And we get x squared minus 2/3 x plus y squared plus 10/3 y minus 2/3 equals 0. Completing the square, it's x minus 1/3 squared plus 1/9 plus y plus 5/3 squared minus 25/9. So that's minus, sorry. 25/9 minus 2/3 equals 0. And therefore, x minus 1/3 squared plus y plus 5/3 squared equals, that's 4, what, 6/9. So 31 ninths. 32 ninths, of course. And yeah, so the it's a circle, center 1/3 negative 5/3, and radius is 4√2/3. Brilliant. 4√2. Excellent. And I haven't made a mistake. And finally, this. Find the image of a line under the transformation. Okay. So we have a line and we are applying a transformation. So how does that work? Well, we have, let's first of all draw the line. Real is equal to 1. That means the real part of W is 1 and imaginary part of W, it can be anything. So let's just call it T. And we can draw this line. It's a vertical line. So real part of W is 1. Okay. Now Z, so in other words, W can be written as 1 plus IT, where T is any real number. Any real number. Yeah, because if you think about it, that's the equation of that line, right? So it's 1 plus IT, right? And now what I'm going to do is substitute that into Z. So Z is equal to 1 over 1 plus IT. And okay, so now I'm going to simplify that. Z equals, and Z equals, and multiply both sides by, so 1 minus IT divided by 1 plus IT, 1 minus IT, and 1 minus IT divided by 1 plus T squared. Yep, which equals to 1 over 1 plus T squared minus T over 1 plus T squared multiplied by I. Okay. And, well, we know that this is equal to X. This is X and this is Y, or IY. So we can attempt, we can say 1 over 1 plus T squared equals X, and T minus T over 1 plus T squared equals Y. If we multiply, but we're trying to eliminate T. So what can we do? Um, oh, okay, of course. We can 1 plus T squared equals 1 over X. T squared is 1 over X minus 1. And we can substitute that into here. Um, okay, so here we can say T. Okay, minus T is equal to Y 1 plus T 1 plus T squared. And 1 plus T squared is 1 over X. So minus T equals Y multiplied by 1 over X. Now, if we multiply this, if we square both sides, we get T squared equals Y squared over X squared. And this is 1 over X minus 1 equals Y squared over X squared. And hopefully, yay, yes, sorry. Multiply everything by X squared. X minus X squared equals Y squared. Move everything to the right. X squared plus Y squared minus X equals 0. Combining X minus X squared minus X plus a quarter, this is a complete square, minus a quarter plus Y squared equals 0. So X minus a half squared plus Y squared equals a quarter, and that is a circle. So the transformation transforms a straight line into a circle with center 1/2 0 and radius 1/2. So how does that look like? Well, we start off by, this is 1, so R real of W is 1. It transforms into 1/2 0 into this. into this circle. Right. And that's modulus z minus a half is a half. That's the equation of that circle. Lovely. Okay. I hope that makes some sort of sense. I hope that is helpful. Sorry about the problem with the circle. I'm not sure what happened. I'm still a bit fuzzy on where the minus come from. And yeah, so I'll see you all. Okay, let's double check. I'm sorry for the mistake in the timetable. So the next webinar is going to be on the 20th, so that's next week, apparently. Yeah, so I'll see you all next week for a webinar on electromagnetic induction. Okay, and enjoy the assignment, and see you all in a week.